by the O's and crosses. In unsupervised learning, we're given data that isn't associated with any output labels Y. Say you're given data on patients and their tumor size and the patient's age, but not whether the tumor was benign or malignant. So the dataset looks like this on the right. We're not asked to diagnose whether the tumor is benign or malignant because we're not given any labels Y in the dataset. Instead, our job is to find some structure or some pattern or just find something interesting in the data. This is unsupervised learning. We call it unsupervised because we're not trying to supervise the algorithm to give some quote right answer for every input. Instead, we ask the algorithm to figure out all by itself what's interesting or what patterns or structures there might be in this data. With this particular dataset, an unsupervised learning algorithm might decide that the data can be assigned to two different groups or two different clusters. And so it might decide that there's one cluster or group over here, and there's another cluster or group over here. This is a particular type of unsupervised learning called a clustering algorithm because it places the unlabeled data into different clusters. And this turns out to be used in many applications. For example, clustering is used in Google News. What Google News does is every day it goes and looks at hundreds of thousands of news articles on the internet and groups related stories together. For example, here's a sample from Google News where the headline of the top article is "Giant Panda Gives Birth to Rare Twin Cubs at Japan's Oldest Zoo." This article had actually caught my eye because my daughter loves pandas, and so there are a lot of stuffed panda toys and watching of panda videos in my house. And looking at this, you might notice that below this are other related articles. Maybe from the headlines alone, you can start to guess what clustering might be doing. Notice that the word panda appears here, 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 and here. And notice that the word twin also appears in all 5 articles. And the word zoo also appears in all of these articles. So the clustering algorithm is finding articles out of all the hundreds of thousands of news articles on the internet that day, finding the articles that mention similar words and grouping them into clusters. Now, what's cool is that this clustering algorithm figures out on its own which words suggest that certain articles are in the same group. What I mean is there isn't an employee at Google News who's telling the algorithm to find articles that have the word panda and twins and zoo zoo to put them into the same cluster. The news topics change every day, and there are so many news stories, it just isn't feasible to have people doing this every single day for all the topics the news covers. Instead, the algorithm has to figure out on its own, without supervision, what are the clusters of news articles today. So that's why this clustering algorithm is a type of unsupervised learning algorithm. Let's look at a second example of unsupervised learning applied to clustering genetic or DNA data. This image shows a picture of DNA microarray data. These look like tiny grids of a spreadsheet, and each tiny column represents the genetic or DNA activity of one person. So, for example, this entire column here is from one person's DNA, and this other column is of another person. Each row represents a particular gene. So just as an example, perhaps this row here might represent a gene that affects eye color, or this row here is a gene that affects how tall someone is. Researchers have even found a genetic link to whether someone dislikes certain vegetables, such as broccoli or Brussels sprouts or asparagus. So next time someone asks you, why didn't you finish your salad? You can tell them, oh, maybe it's genetic. For DNA microarrays, the idea is to measure how much certain genes are expressed for each individual person. So these colors, red, green, gray, and so on, show the degree to which different individuals do or do not have a specific gene active. And what you can do is then run a clustering algorithm to group individuals into different categories or different types of people. Like maybe these individuals are grouped together, and let's just call this type 1. And these people are grouped into type 2. And these people are grouped as type 3. This is unsupervised learning because we're not telling the algorithm in advance that there is a type 1 person with certain characteristics or a type 2 person with certain characteristics. Instead, what we're saying is, here's a bunch of data. I don't know what the different types of people are, but can you automatically find structure in the data and automatically figure out what are the major types of individuals? Since we're not giving the algorithm the right answer for the examples in advance, this is unsupervised learning. Here's a third example. Many companies have huge databases of customer information. Given this data, can you automatically group your customers into different market segments so that you can more efficiently serve your customers? Concretely, the deeplearning.ai team did some research to better understand the deeplearning.ai community and why different individuals take these classes, subscribe to the Batch weekly newsletter, or attend our Pioneer events. Let's visualize the deeplearning.ai community as this collection of people. Running clustering, that is market segmentation, found a few distinct groups of individuals. One group's primary motivation is seeking knowledge to grow their skills. Perhaps this is you, and if so, that's great. A second group's primary motivation is looking for a way to develop their career. Maybe you want to get a promotion or a new job or make some career progression. If this describes you, that's great too. And yet another group wants to stay updated on how AI impacts their field of work. Perhaps this is you. That's great too. This is a clustering that our team used to try to better serve our community as we're trying to figure out what are the major categories of learners in the deeplearning.ai community. So if any of these is your top motivation for learning, that's great, and I hope I'll be able to help you on your journey. In the last video, you saw what is unsupervised learning and one type of unsupervised learning called clustering. Let's give a slightly more formal definition of unsupervised learning and take a quick look at some other types of unsupervised learning other than clustering. Whereas in supervised learning, the data comes with both inputs X and output labels Y, in unsupervised learning, the data comes only with inputs X but not output labels Y, and the algorithm has to find some structure or some pattern or something interesting in the data. We've seen just one example of unsupervised learning called a clustering algorithm, which groups similar data points together. In this specialization, you learn about clustering as well as two other types of unsupervised learning. One is called anomaly detection, which is used to detect unusual events. This turns out to be really important for fraud detection in the financial system, where unusual events, unusual transactions could be signs of fraud, and for many other applications. And you also learn about dimensionality reduction. This lets you take a big data set and almost magically compress it to a much smaller data set while losing as little information as possible. In case anomaly detection and dimensionality reduction don't seem to make too much sense to you yet, don't worry about it. We'll get to this later in this specialization. Now, I'd like to ask you another question to help you check your understanding. And no pressure, if you don't get it right on the first try, it's totally fine. Please select any of the following that you think are examples of unsupervised learning. 2 are unsupervised examples, and 2 are supervised learning examples. So please take a look. Maybe you remember the spam filtering problem. If you have labeled data, labeled as spam or non-spam email, you can treat this as a supervised learning problem. The second example, the news story example, that's exactly the Google News and Tandem example that you saw in the last video. And so you can approach that using a clustering algorithm to group news articles together. So that would use unsupervised learning. The market segmentation example that I talked about a little bit earlier, you can do that as an unsupervised learning problem as well, because you can give your algorithm some data and ask it to discover market segments automatically. And the final example on diagnosing diabetes. Well, actually, that's a lot like our breast cancer example from the supervised learning videos. Only instead of benign or malignant tumors, we instead have diabetes or not diabetes. And so you can approach this as a supervised learning problem, just like we did for the breast tumor classification problem. Even though in the last video, we've talked mainly about clustering, in later videos in this specialization, we'll dive much more deeply into anomaly detection and dimensionality reduction as well. So that's unsupervised learning. Before we wrap up this section, I want to share with you something that I find really exciting and useful, which is the use of Jupyter notebooks in machine learning. Let's take a look at that in the next video. So far in the videos, you've seen supervised learning and unsupervised learning, and also examples of both. For you to more deeply understand these concepts, I'd like to invite you in this class to see, run, and maybe later write code yourself to implement these concepts. The most widely used tool by machine learning and data science practitioners today is the Jupyter Notebook. This is the default environment that a lot of us use to code up and experiment and try things out. And so in this class, right here in your web browser, you'll be able to use a Jupyter Notebook environment to test out some of these ideas for yourself as well. This is not some made up, simplified, environment. This is the exact same environment, the exact same tool, the Jupyter Notebook that developers are using in many large companies right now. One type of lab that you see throughout this class are optional labs, which are ones you can open and run one line at a time with usually not needing to write any code yourself. So optional labs are designed to be very easy, and I can guarantee you will get full marks for every single one of them because there are no marks. All you need to do is open it up and just run the code we've provided. And by reading through and running the code in the optional labs, you see how machine learning code runs. And you should be able to complete them, relatively quickly. just by running it one line at a time from top to bottom. Optional labs are completely optional, so you don't have to do them at all if you don't want to. But I hope you will take a look, because running through them will give you a deeper feel, give you a little bit more experience with what machine learning algorithms, what machine learning code actually looks like. Starting next week, there'll also be some practice labs, which will give you an opportunity to write some of that code yourself. But we'll get to that next week, so don't worry about it for now. And I hope you just go through the next optional lab and get through the rest of the content for this week. So let's take a look at an example of a notebook. Here's what you see when you go to the first optional lab. Feel free to scroll up and down and browse and mouse over the different menus and take a look at the different options here. You might notice that there are two types of these blocks, also called cells, in the notebook. And there are two types of cells. One is what's called a markdown cell, which means basically a bunch of text. So here you can actually edit the text if you don't like the text that we wrote. But this is text that describes the code. Then there's a second type of block or cell, which looks like this, which is a code cell. So here we've already provided the code, and if you want to run this code cell, hitting Shift-Enter will run the code in this code cell. Oh, and by the way, if you click on the markdown cell, so it's showing all this formatting, go ahead and hit Shift-Enter on your keyboard as well, and that will also convert it back to this nicely formatted text. This optional lab shows some common Python code, so you can go ahead and run this afterward in your own Jupyter notebook. When you jump into this notebook yourself, what I'd like you to do is select the cells and hit Shift-Enter. Well, read through the code, see if it makes sense. Try to make a prediction about what you think this code will do, and then hit Shift-Enter. And then see what the code actually does. And if you feel like it, feel free to go in and edit the code. Change the code and then run it and see what happens. And if you haven't played in a Jupyter Notebook environment before, I hope you become more familiar with Python in a Jupyter Notebook. I spend a lot of hours playing around in Jupyter Notebooks, and so I hope you have fun with them too. And after that, I look forward to seeing you in the next video, where we'll take the supervised In this video, we'll look at what the overall process of supervised learning is like. Specifically, you see the first model of this course, a linear regression model. That just means fitting a straight line to your data. It's probably the most widely used learning algorithm in the world today. And as you get familiar with linear regression, many of the concepts you see here will also apply to other machine learning models that you see later in this specialization. Let's start with a problem that you can address using linear regression. Say you want to predict the price of a house based on the size of a house. This is an example we've seen earlier this week. We're going to use a dataset on house sizes and prices from Portland, a city in the United States. Here we have a graph where the horizontal axis is the size of the house in square feet, and the vertical axis is the price of the house in thousands of dollars. Let's go ahead and plot the data points for various houses in the dataset. Here, each data point, each of these little crosses, is a house with a size and a price that it most recently was sold for. Now, let's say you're a real estate agent in Portland, and you're helping a client sell her house. And she's asking you, how much do you think you can get for this house? This dataset might help you estimate the price she could get for it. You start by measuring the size of the house, and it turns out that her house is 1,250 square feet. How much do you think this house could sell for? One thing you could do is you can build a linear regression model from this dataset. Your model will fit a straight line to the data, which might look like this. And based on this straight line fit to the data, you can kind of see that if a house is 1,250 square feet, it will intersect the best fit line over here. And if you trace that to the vertical axis on the left, you can see the prices maybe around here, say about $220,000. So this is an example of what's called a supervised learning model. We call this supervised learning because you are first training your model by giving it data that has the right answers. Because you give the model examples of houses with both the size of the house as well as the price that the model should predict for each house. Where here the prices, that is, the right answers, are given for every house in the dataset. This linear regression model is a particular type of supervised learning model. It's called a regression model because it predicts numbers as the output, like prices in dollars. Any supervised learning model that predicts a number, such as 220,000 or 1.5 or negative 33.2, is addressing what's called a regression problem. So linear regression is one example of a regression model, but there are other models for addressing regression problems too. And we'll see some of those later in course 2 of this specialization. And just to remind you, in contrast with the regression model, the other most common type of supervised learning model is called a classification model. A classification model predicts categories or discrete categories, such as predicting if a picture is of a cat, meow, or a dog, woof. Or if given a medical record, it has to predict if a patient has a particular disease. You see more about classification models later in this course as well. So as a reminder about the difference between classification and regression, in classification, there are only a small number of possible outputs. If your model is recognizing cats versus dogs, that's 2 possible outputs. Or maybe you're trying to recognize any of 10 possible medical conditions in a patient. So if there's a discrete, finite set of possible outputs, we call it a classification problem, whereas in regression, there are infinitely many possible numbers that the model could output. In addition to visualizing this data as a plot here on the left, there's one other way of looking at the data that would be useful, and that's a data table here on the right. The data comprises a set of inputs. This would be the size of the house, which is this column here. It also has outputs. You're trying to predict the price, which is this column here. Notice that the horizontal and vertical axes correspond to these 2 columns, the size and the price. And so if you have, say, 47 rows in this data table, then there are 47 of these little crosses on the plot of the left, each cross corresponding to 1 row of the table. For example, the first row of the table is a house with size 2,104 square feet, so that's around here. And this house sold for $400,000, which is around here. So this first row of the table is plotted as this data point over here. Now, let's look at some notation for describing the data. This is notation that you find useful throughout your journey in machine learning. As you increasingly get familiar with machine learning terminology, this will be terminology that you can use to talk about machine learning concepts with others as well, since a lot of this is quite standard across AI. You'll be seeing this notation multiple times in this specialization, so it's okay if you don't remember everything the first time through. It will naturally become more familiar over time. The dataset that you just saw and that is used to train the model is called a training set. Note that your client's house is not in this dataset because it's not yet sold, so no one knows what its price is. So to predict the price of your client's house, you first train your model to learn from the training set, and that model can then predict your client's house's price. In machine learning, the standard notation to denote the input here is lowercase x, and we call this the input variable. It's also called a feature or an input feature. For example, for the first house in your training set, x is the size of the house, so x equals 2,104. The standard notation to denote the output variable, which you're trying to predict, which is also sometimes called the target variable, is lowercase y. And so here, y is the price of the house, and for the first training example, this is equal to 400. So y equals 400. So the dataset has one row for each house, and in this particular training set, there are 47 rows, with each row representing a different training example. We're going to use lowercase m to refer to the total number of training examples, and so here, m is equal to 47. To indicate a single training example, we're going to use the notation parentheses x comma y. So for the first training example, x comma y, this pair of numbers is 2,104, 400. Now, we have a lot of different training examples. We have 47 of them, in fact. So to refer to a specific training example, this will correspond to a specific row in this table on the left. I'm going to use the notation x superscript in parentheses I, comma, y superscript in parentheses I. The superscript tells us that this is the ith training example, such as the first, second, or third up to the 47th training example. I here refers to a specific row in the table. So, for instance, here is the first example when I equals 1 in the training set. And so x superscript 1 is equal to 2,104, and y superscript 1 is equal to 400. And let's add the superscript 1 here as well. Just a note, this superscript I in parentheses is not exponentiation. So when I write this is not x squared. This is not x to the power of 2. It just refers to the second training example. So this I is just an index in the training set and refers to row I in the table. In this video, you saw what a training set is like, as well as a standard notation for describing this training set. In the next video, let's look at what it'll take to take this training set that you just saw and feed it to a learning algorithm so that the algorithm can learn from this data. Let's see that in the next video. Let's look in this video at the process of how supervised learning works. Supervised learning algorithm will input a data set, and then what exactly does it do and what does it output? Let's find out in this video. Recall that a training set in supervised learning includes both the input features, such as the size of the holes, and also the output targets, such as the price of the holes. The output targets are the right answers that the model will learn from. To train the model, you feed the training set both the input features and the output targets to your learning algorithm. Then, your supervised learning algorithm will produce some function. We'll write this function as lowercase f, where f stands for function. Historically, this function used to be called a hypothesis, but I'm just going to call it a function f in this class. And the job of f is to take a new input x and output an estimate or prediction, which I'm going to call y hat. And it's written like the variable y with this little hat symbol on top. In machine learning, the convention is that y hat is the estimate or the prediction for y. The function f is called the model. X is called the input or the input feature, and the output of the model is the prediction y hat. The model's prediction is the estimated value of y. When the symbol is just the letter y, then that refers to the target, which is the actual true value in the training set. In contrast, y hat is an estimate. It may or may not be the actual true value. Well, if you're helping your client to sell their hulls, well, the true price of the hulls is unknown until they sell it. So your model f, given the size, outputs a price which is the estimated, that is the prediction of what the true price will be. Now, when we design a learning algorithm, a key question is, how are we going to represent the function f? Or in other words, what is the math formula we're going to use to compute f? For now, let's stick with f being a straight line. So your function can be written as f subscript w comma b of x equals, I'm going to use w times x plus b. I'll define a portrait. Let's look in this video at the process of how supervised learning works. Supervised learning algorithm will input a data set, and then what exactly does it do and what does it output? Let's find out in this video. Recall that a training set in supervised learning includes both the input features, such as the size of the hulls, and also the output targets, such as the price of the hulls. The output targets are the right answers that the model will learn from. To train the model, you feed the training set both the input features and the output targets to your learning algorithm. Then, your supervised learning algorithm will produce some function. We'll write this function as lowercase f, where f stands for function. Historically, this function used to be called a hypothesis, but I'm just going to call it a function f in this class. And the job of f is to take a new input x and output an estimate or prediction, which I'm going to call y hat. And it's written like the variable y with this little hat symbol on top. In machine learning, the convention is that y hat is the estimate or the prediction for y. The function f is called the model. X is called the input or the input feature, and the output of the model is the prediction y hat. The model's prediction is the estimated value of y. When the symbol is just the letter y, then that refers to the target, which is the actual true value in the training set. In contrast, y hat is an estimate. It may or may not be the actual true value. Well, if you're helping your client to sell their hulls, well, the true price of the hulls is unknown until they sell it. So your model F, given the size, outputs a price which is the estimated, that is the prediction of what the true price will be. Now, when we design a learning algorithm, a key question is, how are we going to represent the function f? Or in other words, what is the math formula we're going to use to compute f? For now, let's stick with f being a straight line. So your function can be written as f subscript w comma b of x equals, I'm going to use w times x plus b. I'll define w and b soon, but for now, just know that w and b are numbers, and the values chosen for w and b will determine the prediction y hat based on the input feature x. So this fwb of x means f is a function that takes x as input, and depending on the values of w and b, f will output some value of a prediction y hat. As an alternative to writing this fw comma b of x, I'll sometimes just write f of x without explicitly including w and b in the subscript. It's just a simpler notation, but means exactly the same thing as fwb of x. Let's plot the training set on the graph where the input feature x is on the horizontal axis and the output target y is on the vertical axis. Remember, the algorithm learns from this data and generates a best fit line, like maybe this one here. This straight line is the linear function fwb of x equals w times x plus b, the vertical axis. Remember, the algorithm learns from this data and generates a best fit line, like maybe this one here. This straight line is the linear function fwb of x equals w times x plus b. Or more simply, we can drop w and b and just write f of x equals wx plus b. Here's what this function is doing. It's making predictions for the value of y using a straight line function of x. So you may ask, why are we choosing a linear function where linear function is just a fancy term for a straight line instead of some nonlinear function like a curve or a parabola? Well, sometimes you want to fit more complex nonlinear functions as well, like a curve like this. But since this linear function is relatively simple and easy to work with, let's use a line as a foundation that will eventually help you to get to more complex models that are nonlinear. This particular model has a name. It's called linear regression. More specifically, this is linear regression with one variable, where the phrase one variable means that there's a single input variable or feature x, namely the size of the host. Another name for a linear model with one input variable is univariate linear regression, where uni means one in Latin and where variate means variable. So univariate is just a fancy way of saying one variable. In a later video, you'll also see a variation of regression where you want to make a prediction based not just on the size of a house, but on a bunch of other things that you may know about the house, such as the number of bedrooms and other features. And by the way, when you're done with this video, there is another optional lab. You don't need to write any code. Just review it, run the code, and see what it does. That will show you how to define in Python a straight line function. And the lab will let you choose the values of W and B to try to fit the training data. You don't have to do the lab if you don't want to, but I hope you play with it when you're done watching this video. So that's linear regression. In order for you to make this work, one of the most important things you have to do is construct a cost function. The idea of a cost function is one of the most universal and important ideas in machine learning, and is used in both linear regression and in training many of the most advanced AI models in the world. So let's go on to the next video and take a look at how you In order to implement linear regression, the first key step is for us to define something called a cost function. This is something we'll build in this video. And the cost function will tell us how well the model is doing so that we can try to get it to do better. Let's look at what this means. Recall that you have a training set that contains input features X and output targets Y. And the model you're going to use to fit this training set is this linear function f(wb) of x equals w times x plus b. To introduce a little bit more terminology, the w and b are called the parameters of the model. In machine learning, parameters of a model are the variables you can adjust during training in order to improve the model. Sometimes you also hear the parameters w and b referred to as coefficients or as weights. Now, let's take a look at what these parameters w and b do. Depending on the values you've chosen for w and b, you get a different function f of x, which generates a different line on the graph. And remember that we can write f of x as a shorthand for fwb of x. We're going to take a look at some plots of f of x on a chart. Maybe you're already familiar with drawing lines on charts, but even if this is a review for you, I hope this will help you build intuition on how w and b, the parameters, determine f. When w is equal to 0 and b is equal to 1.5, then f looks like this horizontal line. In this case, the function f of x is 0 times x plus 1.5, so f is always a constant value. It always predicts 1.5 for the estimated value of y. So y hat is always equal to b, and here b is also called the y-intercept because that's where it crosses the vertical axis or the y-axis on this graph. As a second example, if w is 0.5 and b is equal to 0, then f of x is 0.5 times x. When x is 0, the prediction is also 0, and when x is 2, then the prediction is 0.5 times 2, which is 1. So you get a line that looks like this. And notice that the slope is 0.5 divided by 1. So the value of w gives you the slope of the line, which is 0.5. And finally, if w equals 0.5 and b equals 1, then f of x is 0.5 times x plus 1. And when x is 0, then f of x equals b, which is 1. So the line intersects the vertical axis at b, the y-intercept. Also, when x is 2, then f of x is 2. So the line looks like this. Again, the slope is 0.5 divided by 1, so the value of w gives you the slope, which is 0.5. Recall that you have a training set, like the one shown here. With linear regression, what you want to do is to choose values for the parameters w and b, so that the straight line you get from the function f somehow fits the data well, like maybe this line shown here. And when I say that the line fits the data, visually you can think of this to mean that the line defined by f is roughly passing through or somewhat close to the training examples as compared to other possible lines that are not as close to these points. And just to remind you of some notation, a training example like this point here is defined by x superscript I, y superscript I will be true, then f of x is 2. So the line looks like this. Again, the slope is 0.5 divided by 1, so the value of w gives you the slope, which is 0.5. Recall that you have a training set, like the one shown here. With linear regression, what you want to do is to choose values for the parameters w and b so that the straight line you get from the function f somehow fits the data well, like maybe this line shown here. And when I say that the line fits the data, visually you can think of this to mean that the line defined by f is roughly passing through or somewhat close to the training examples as compared to other possible lines that are not as close to these points. And just to remind you of some notation, a training example like this point here is defined by x superscript I, y superscript I, where y is the target. For a given input xi, the function f also makes a predicted value for y, and the value that it predicts for y is y hat I, shown here. For our choice of a model, f of xi is w times xi plus b. Stated differently, the prediction y hat I is f of wb of xi, where for the model we're using, f of xi is equal to wxi plus b. So now the question is, how do you find values for w and b so that the prediction y hat I is close to the true target yi for many or maybe all training examples xi, yi? To answer that question, let's first take a look at how to measure how well a line fits the training data. To do that, we're going to construct our cost function. The cost function takes the prediction y hat and compares it to the target y by taking y hat minus y. This difference is called the error. We're measuring how far off the prediction is from the target. Next, let's compute the square of this error. Also, we're going to want to compute this term for different training examples I in the training set. So when measuring the error for example I, we'll compute this squared error term. Finally, we want to measure the error across the entire training set. In particular, let's sum up the squared errors like this. We'll sum from I equals 1, 2, 3, all the way up to m. And remember that m is the number of training examples, which is 47 for this dataset. Notice that if we have more training examples, m is larger, and your cost function will calculate a bigger number since it's summing over more examples. So to build a cost function that doesn't automatically get bigger as the training set size gets larger, by convention, we will compute the average squared error instead of the total squared error, and we do that by dividing by m like this. Okay, we're nearly there. Just one last thing. By convention, the cost function that machine learning people use actually divides by 2 times m. The extra division by 2 is just meant to make some of our later calculations a little bit neater, but the cost function still works whether you include this division by 2 or not. So this expression right here is the cost function, and we're going to write j of wb to refer to the cost function. This is also called the squared error cost function, and it's called this because you're taking the square of these error terms. In machine learning, different people will use different cost functions for different applications, but the squared error cost function is by far the most commonly used one for linear regression, and for that matter for all regression problems, where it seems to give good results for many applications. So just as a reminder, the prediction y hat is equal to the output of the model f at x. So we can rewrite the cost function j of wb as 1 over 2m times the sum from I equals 1 to m of f of x I minus yi is all regress to the output of the model f at x. So we can rewrite the cost function j of wb as 1 over 2m times the sum from I equals 1 to m of f of x I minus yi, the quantity squared. Eventually, we're going to want to find values of w and b that make the cost function small. But before going there, let's first gain more intuition about what j of wb is really computing. At this point, you might be thinking, we've done a whole lot of math to define the cost function, but what exactly is it doing? Let's go on to the next video where we'll step through one example. Of what the cost function is really computing that I hope will help you build intuition about what it means if j of wb is large versus if the cost j is small. Let's go on. On to the next video. We've seen the mathematical definition of the cost function. Now, let's build some intuition about what the cost function is really doing. In this video, we'll walk through one example to see how the cost function can be used to find the best parameters for your model. I know this video is a little bit longer than the others, but bear with me, I think it'll be worth it. To recap, here's what we've seen about the cost function so far. You want to fit a straight line to the training data, so you have this model fwb of x is w times x plus b. And here, the model's parameters are w and b. Now, depending on the values chosen for these parameters, you get different straight lines, like this. And you want to find values for w and b so that the straight line fits the training data well. To measure how well a choice of w and b fits the training data, you have a cost function j. And what the cost function j does is, it measures the difference between the model's predictions and the actual true values for y. What you see later is that linear regression would try to find values for w and b that make j of w be as small as possible. In math, we write it like this. We want to minimize j as a function of w and b. So now, in order for us to better visualize the cost function j, let's work with a simplified version of the linear regression model. We're going to use the model fw of x is w times x. You can think of this as taking the original model on the left and getting rid of the parameter b, or setting the parameter b equal to 0, so it just goes away from the equation. So f is now just w times x. So you now have just one parameter w, and your cost function j looks similar to what it was before, taking the difference and squaring it, except that now f is equal to w times xi, and j is now a function of just w. And the goal becomes a little bit different as well, because you have just one parameter w, not w and b. So with this simplified model, the goal is to find a value for w that minimizes j of w. To see this visually, what this means is that if b is set to 0, then f defines a line that looks like this. And you see that the line passes through the origin here, because when x is 0, well, f of x is 0 too. Now, using this simplified model, let's see how the cost function changes as you choose different values for the parameter w. In particular, let's look at graphs of the model f of x and the cost function j. I'm going to plot these side by side, and you'll be able to see how the two are related. First, notice that for f subscript w, when the parameter w is fixed, that is always a constant value, then fw is only a function of x, which means that the estimated value of y depends on the value of the input x. For function, because when x is 0, well, f of x is 0 too. Now, using this simplified model, let's see how the cost function changes as you choose different values for the parameter w. In particular, let's look at graphs of the model f of x and the cost function j. I'm going to plot these side by side, and you'll be able to see how the two are related. First, notice that for f subscript w, when the parameter w is fixed, that is always a constant value, then fw is only a function of x, which means that the estimated value of y depends on the value of the input x. In contrast, looking to the right, the cost function j is a function of w, where w controls the slope of the line defined by fw. So the cost defined by j depends on a parameter, in this case, the parameter w. So let's go ahead and plot these functions fw of x and j of w side by side so that we can see how they are related. We'll start with the model, that is the function fw of x on the left. Here, the input feature x is on the horizontal axis, and the output value y is on the vertical axis. Here's a plot of 3 points representing the training set at positions 1, 1, 2, 2, and 3, 3. Let's pick a value for w. Say w is 1. So for this choice of w, the function fw looks like this straight line with a slope of 1. Now, what you can do next is calculate the cost j when w equals 1. So you may recall that the cost function is defined as follows. Is the squared error cost function. So if you substitute fw of xi with w times xi, the cost function looks like this, where this expression is now w times xi minus yi. So for this value of w, it turns out that the error term inside the cost function, this w times xi minus yi, is equal to 0 for each of the 3 data points. Because for this data set, when x is 1, then y is 1. When w is also 1, then f of x equals 1. So f of x equals y for this first training example, and the difference is 0. Plugging this into the cost function j, you get 0 squared. Similarly, when x is 2, then y is 2, and f of x is also 2. So again, f of x equals y for the second training example. In the cost function, the squared error for the second example is also 0 squared. Finally, when x is 3, then y is 3, and f of 3 is also 3. In the cost function, the third squared error term is also 0 squared. So for all 3 examples in this training set, f of xi equals yi for each training example I. So f of xi minus yi is 0. So for this particular data set, when w is 1, then the cost j is equal to 0. Now, what you can do on the right is plot the cost function j. And notice that because the cost function is a function of the parameter w, the horizontal axis is now labeled w and not x. And the vertical axis is now j and not y. So you have j of 1 equals to 0. In other words, when w equals 1, j of w is 0. So let me go ahead and plot that. Now let's look at how f and j change for different values of w. W can take on a range of values, right? So w can take on negative values, w can be 0, and it can take on positive values too. So what if w is equal to 0.5 instead of 1? What will these graphs look like then? Let's go ahead and plot that. So let's set w to be equal to 0.5. And in this case, the function f of x now looks like this, is a line with a slope equal to 0.5. And let's also compute the cost j when w is 0.5. Recall that the cost function is measuring the squared error or difference between the estimated value, that is y hat I, which is f of xi, and the true value, that is yi, for each example I. So visually, you can see that the error or difference is equal to the height of this vertical line here when x is equal to 1, because this little line is the gap between the actual value of y and the value that the function f predicted, which is a bit further down here. So for this first example, when x is 1, f of x is 0.5. So the squared error on the first example is 0.5 minus 1 squared. Remember, the cost function will sum over all the training examples in the training set. So let's go on to the second training example. When x is 2, the model is predicting f of x is 1. And the actual value of y is 2. So the error for the second example is equal to the height of this little line segment here. And the squared error is the square of the length of this line segment. So you get 1 minus 2 squared. Let's do the third example. Repeating this process, the error here, also shown by this line segment, is 1.5 minus 3 squared. Next, we sum up all of these terms, which turns out to be equal to 3.5. Then we multiply this term by 1 over 2m, where m is the number of training examples. Since there are 3 training examples, m equals 3. So this is equal to 1 over 2 times 3, where this m here is 3. If we work out the math, this turns out to be 3.5 divided by 6. So the cost j is about 0.58. Let's go ahead and plot that over there on the right. Okay? Now let's try one more value for w. How about if w equals 0? What do the graphs for f and j look like when w is equal to 0? It turns out that if w is equal to 0, then f of x is just this horizontal line that is exactly on the x-axis. And so the error for each example is a line that goes from each point down to the horizontal line that represents f of x equals 0. So the cost j when w equals 0 is 1 over 2m times the quantity 1 squared plus 2 squared plus 3 squared, and that's equal to 1 over 6 times 14, which is about 2.33. So let's plot this point where w is 0 and j of 0 is 2.33 over here. And you can keep doing this for other values of w. Since w can be any number, it can also be a negative value. So if W is negative 0.5, then the line F is a downward sloping line like this. It turns out that when W is negative 0.5, then you end up with an even higher cost around 5.25, which is this point up here. And you can continue computing the cost function for different values of W and so on and plot these, right? So it turns out that by computing a range of values, you can slowly trace out what the cost function J looks like. And that's what J is. To recap, each value of parameter W corresponds to a different straight line fit, f of x, on the graph to the left. And for the given training set, that choice for a value of W corresponds to a single point on the graph on the right. Because for each value of W, you can calculate the cost J of W. For example, when W equals 1, this corresponds to this straight line fit through the data, and it also corresponds to this point on the graph of J, where W equals 1 and the cost J of 1 equals 0. Whereas when W equals 0.5, this gives you this line, which has a smaller slope. And this line, in combination with the training set, corresponds to this point on the cost function graph at W equals 0.5. So for each value of W, you wind up with a different line and its corresponding cost J of W. And you can use these points to trace out this plot on the right. Given this, how can you choose the value of W that results in the function f fitting the data well? Well, as you can imagine, choosing a value of W that causes J of W to be as small as possible seems like a good bet. J is the cost function that measures how big the squared errors are, so choosing W that minimizes these squared errors, makes them as small as possible, would give us a good model. In this example, if you were to choose the value of W that results in the smallest possible value of J of W, you'd end up picking W equals 1. And as you can see, that's actually a pretty good choice. This results in a line that fits the training data very well. So that's how, in linear regression, you use the cost function to find the value of W that minimizes J. Or in the more general case, when we had parameters W and B rather than just W, you find the values of W and B that minimize J. So to summarize, you saw plots of both F and J and work through how the two are related. As you vary W or vary W and B, you end up with different straight lines. And when that straight line passes close to the data, the cost J is small. So the goal of linear regression is to find the parameters W or W and B that results in the smallest possible value for the cost function J. Now in this video, we worked through our example with a simplified problem using only W. In the next video, let's visualize what the cost function looks like for the full version of linear regression using both W and B. And you see some cool 3D plots. Let's go to the next video.